So this is our last video cast in chapter 16, and we're going to focus on salts. And we're going to take a look at how salts can be defined as acid or base solutions. But first, a little chemistry in your everyday life. I'm going to zoom in on this, and we're going to talk about amines and amine hydrochlorides. So many low molecular weight amines have a fishy odor. Amines in NH3 are produced by the anaerobic, absence of water, decomposition of dead animal or plant matter. Two such amines are very disagreeable and have not very nice aromas: putrescine and cadaverine. The names of these substances are testaments to their repugnant odors. Many drugs, including quinine, codeine, caffeine, amphetamine, are also amines. And like amines, these substances are weak bases, and the amine nitrogen is readily protonated or given a hydrogen upon treatment with an acid. The resulting products are called acid salts, and that's what we're going to learn about today, is salts. If we use A as the abbreviation for amine, the acid salt formed by the reaction of hydrochloric acid can be written A, amine with H plus and Cl minus. It can be also written as AHCl and referred to as a hydrochloride. Amphetamine hydrochloride, for example, is the acid salt formed by treating amphetamine with HCl. So here's amphetamine, they treat it with some HCl, and now we've got the NH3 plus right here because it gained a hydrogen, and the Cl minus right here. Acid salts are much less volatile and more stable and more water soluble than corresponding amines. For this reason, many drugs that are amines are sold and administered as salts. Some examples of over-the-counter medications that contain amine hydrochlorides as active ingredients are below. So you can see Sudafed right here, which usually contains an amphetamine, and then some of these other ones also have hydrochloride salts of amines in them as well. Take a look at one of your medicines and look on the back, and you'll probably notice that it contains a hydrogen chloride type salt. So back to what we're going to learn today. We're going to learn about salt solutions, and we're going to take and look at how salt solutions can act as acids or as bases, depending on what they're made out of. So a salt is made of a cation and an anion, a positive ion and a negative anion. Some people call these ionic compounds, which is what a salt actually is. An ionic compound can be soluble or not. We're going to focus on the ones that are soluble today, and if you forgot how we determined that, you can look on your periodic table, and this is where the mainly soluble salts or ionic compounds are. And the one I'd like to highlight for you too is the group 1A, or the NH4 plus ones are always soluble, and you'll see many of them that have sodium, potassium, lithium, rubidium in it, and if it ever has one of those in it, you can be like, oh yeah, soluble, split it up into its ions. These dissociate, aka ionize, into their particular positive and negative cation and anions. So we must look to these ions for their ability to react with H2O, because remember, we're looking at acids and bases being in aqueous solutions or dissolved in water, and so we want to know, when they're dissolved in water, do they gain protons or do they give up protons? The fancy name for this dissolved in water is called hydrolyze, and the ion's ability to get hydrogens or OH minuses allows it to be an acid or a base. So how do you know? How do we know? Well, step number one is to dissociate or split up the salt or ionize it. Step number two is to look at its ions. And there are 4 different cases that can happen in these ions. Case number one is that the positive and the negative ions are from a strong acid or a strong base. These will be neutral. Case number 2 is if the positive ion is from a strong base and the negative ion is from a weak acid. These will act basic. Case number 3 is if the positive ion is from a weak base and the negative ion is from a strong acid. These will act acidic. And the fourth case is the positive ion comes from a weak base, the negative ion comes from a weak acid, and then we can't tell for sure unless we know the Ka and the Kb and the relative strength of these weak acid or base conjugates that are present. So why does this happen? And I'm going to look at a case from each one of these right here and go in depth as to why these will be neutral, these will be basic, and these will be acidic, and write equations to explain that. So case number 1. KBr, ions from a strong acid and a strong base. So K plus came from a strong, well, step number 1, dissociate it. So KBr, of course, forms K plus and Br minus. And right now, maybe is a good time to review which ones are the strong acids and which ones are the strong bases. And I always assume you know Hyber, Hickel, High, Hono, Hickelo, and then H2SO4. But if you don't know those, maybe write those down on a little card, because you got to have those just right on the top of your head. And then you do need to know which ones of the strong bases are as well. And for those, you need a periodic table. And you want to have those memorized as well, that it's lithium, sodium, potassium, rubidium, cesium, calcium, strontium, barium, and the hydroxides of those. Now you can forget the hydroxide part, but you got to know that those elements are from a strong base, and therefore when you dissociate the salt, those are going to do nothing in solution. Anytime you get a strong cation from a strong base, neutral, it'll do nothing. Anytime you get an anion from one of these strong acids, it will do nothing in solution. K plus is from a strong base, KOH. KOH wants to break up to give you K plus and OH minus right here. Therefore, it has no desirability to go backwards. It doesn't want, K plus doesn't want to go get hydrogens. K plus doesn't want to go get OH minuses. It wants to do nothing in solution. Since it came from a strong, it wants to stay that, so K plus is a neutral substance. Looking at Br minus, it came from HBr, and so HBr breaks up to be H plus and Br minus, and once again, it has no desirability to go backwards. Br minus can't go and get H pluses and become HBr. So this is why if a substance has a positive and a negative ion from a strong acid and a strong base, it will be neutral in solution, because those ions, the ions from the periodic table right here in a strong B, have no desire to get back together. They want to be ionized. They want to be broken up. Next case, number 2, a weak acid and a strong base. So here's an example of a salt, NaF, put together from Na, which is from a strong base, NaOH, and a weak acid, F, HF. So Na plus is from a strong base, and so it would split up, and Na then has no desire to go back looking like this at all. F minus, on the other hand, came from a weak acid, HF. And so if you're stuck on these types of things where it asks you, is this acidic, basic, or neutral, just write down the two ions, Na plus and HF, and to the one that's positive, add an OH and ask yourself, is it strong or weak? To the F minus, or to the anion, add an H and ask yourself, is it strong or weak? If the answer is it's weak, then you know you're somewhere where it's going to act acidic or basic. The strong ones, remember, want to remain completely dissociated and don't want to do anything. HF of course, is a weak acid that F minus came from, and so HF technically only slightly ionizes. Its Ka is like 1 times 10 to the negative fifth. It only gives you a little bit of H plus and F minus. It wants to go back together if it can, and so F minus is going to act basic, and it's going to get hydrogens if it can. So that's case number 2, where you have a strong base and a weak acid that make up the salt. Case number 3, weak base and strong acid. So here's NH4Cl. Split it up. You get NH4 plus and Cl minus. And like I said before, if you're not sure where it came from, tack an OH onto here, tack an H onto here. If you recognize that this was from a strong, well then just cross it off right away because you know it's going to do nothing. I don't recognize that as being a strong base, so maybe this came from a weak base. Yes, it did. It came from a weak base called ammonia, NH3. NH3, when it reacts with water, makes some NH4, but remember, this only makes a little bit of this. And so NH4 wants to give up protons if it can to go back to look like the weak base that it came from. And therefore, NH4 is acidic. Cl minus came from a strong acid HCl, and as we've illustrated countless times before now, Cl minus has no desire to go back and look like HCl. So now that we're a little bit dangerous in these 3 areas, I know there's a 4th area, and the 4th area is a weak and a weak, but we're not going to look at those because we have to know the Kas for those. These are the primary 3 that you've got to be able to do. Let's play a little game. Let's play a little game called acid, base, or neutral, and then we'll write the equation with water if it's acidic or basic. So contestant number 1 is the formula BaCH3COO. Acidic, basic, or neutral. Acidic, basic, or neutral. Look over here. Split it up. See where did they come from. I'll wait for 10 seconds and see if you can make a guess. Okay, so Ba, if you put an OH on there, you might recognize, oh, it came from BaOH2. That's a strong base, right? Strong base right here. It's on the B of the periodic table. So I know that I have a strong base in this formula. CH3COO, true, right here. If I put an H on that, I'm not going to recognize that as a strong acid. I might recognize it from our previous work on this being methyl group and ethyl group. Oh, ethanoic acid, C double bond OOH. Sometimes it's called acetic acid, and it's definitely came from a weak acid. So I have a strong base and a weak acid, so this should act basic, and you are correct. It will act basic. Now let's write the equation quick for how it will act basic. This thing right here, CH3COO minus, when in doubt react it with water. Since it's acting basic, it's going to want to get a hydrogen, and so it will form some CH3COOH, and it will form some OH minus right here. Notice the conjugate acid is formed from this species right here, therefore it will act as a base. Contestant number 2, CH3NH3Br. I'll pause for 5 seconds. You see if you can identify this as an acid, a base, or a neutral ionic compound. So step number 1, split it up. Br minus is probably the easiest one. Tack an H on it and you recognize it right now. It's Hibber, so that's going to be from a strong acid, so that's going to do nothing in solution. CH3NH3 positive, though, if you put an OH on that, that does not look like a strong base that you've ever heard of. And so that must have come from a weak base. As a matter of fact, we've talked a lot about these types of things that have N's right here. and this one happens to have an extra H on it, and so this must have come from an amine. Oh yeah, so it's going to be a weak base and a strong acid. It's going to act acidic. Writing the equation for this, CH3NH3 is going to have a positive charge, because remember this is the positive ion right here and this is the negative ion. When in doubt, react it with water, double arrow that. This is going to give up a hydrogen now because it's going to act acidic, and we'll get some H3O plus on this side, and then we'll get some CH3NH2 as the conjugate base of this acid. Last one, NaBr. Acidic, basic, or neutral. Split it up, Na plus and Br minus. Add an OH right here, and you recognize right now that came from NaOH, which is a strong base. And then add an H to this one, HBr. Oh, and you recognize that that came from a strong acid, HBr, so that's going to do nothing in solution. Since both the positive and negative ions came from strong acids and bases, this will be a neutral solution, and there's no equation to write. So in this video cast, you should have learned that salt solutions can be acidic, basic, or neutral. And you have to look at one of the cases right here to decide whether or not they're going to be neutral, because they came from a strong or a weak, a acid, because they, a base, because they had a conjugate from a weak acid, or if they're going to be acidic because they had a conjugate from a weak base in there. Good luck with your salt defining.